Hello, everyone, and welcome to our next FEBio Studio Webinar series. So my name is Steve Moss. I'm the lead software developer of FEBio and FEBio Studio. And today we're going to talk about contact. We're going to continue the conversation we had during the previous webinar on contact, where we talked mostly about some basic contact concepts and how to set up contact problems in FEBio Studio. And today we're going to continue talking about some more advanced contact topics. So to give you a brief overview of what we'll be doing today, so we'll start with a brief recap of the contact formulations in FEBio, and this is mostly for the people who missed the previous webinar. Then we'll spend a few minutes talking about debugging common contact problems. So how can you recognize them and what can you do to address them? Then we'll talk about contact using different kinds of element formulations, namely shells and higher order elements. And then we'll also talk about some specialized contact formulations and under which situations that you might want to use those. And after that, we'll have about a 10 to 15 minute Q&A session. So let's start with a brief recap of the FEBio contact formulations. So there's basically three categories of contact. So there's the rigid contact, which is used to connect a deformable part to a rigid body. There is the tight contact interface, which connects two non-conforming meshes, so meshes that have that don't have a node-to-node correspondence at the contact interface. And then there's the sliding contact, which allows you to, contact objects in contact. They cannot penetrate, but they are allowed to slide and separate from each other. So usually, obviously, there's two contact surfaces involved. So one is referred to as the primary surface. The other is the secondary surface. The main purpose of the primary surface is essentially to do all the contact calculations. So all the most of the integral evaluations are done on the primary surface. And the main purpose of the secondary surface is basically to identify which point of the primary surface are actually in contact. So it does matter which surface you pick for the primary or secondary surface. In general, we recommend that you pick the finer, non-rigid surface as the primary surface. So in order to detect this contact, the contact algorithms have to project the points of the primary surface onto the secondary surface. And the separation between a point and its projection is referred to as the contact gap. So in the tight interface, this would be a vector quantity, essentially the relative position between the primary and the secondary point. For the sliding interface, we usually only care about the scalar value or the signed scalar gap between those 2 points. So FEBio implements several different types of contact formulations, and they mostly differ in how that projection actually happens and how that these integrals actually are evaluated. And for details on that, I won't spend too much time on that in this webinar. If you want to learn more about that, I suggest that you view the previous webinar. So contact is essentially a nonlinear constraint. And so in principle, mathematically speaking, is enforced through a method called Lagrange multipliers. In the case of contact, these Lagrange multipliers have a physical meaning. They are essentially the tractions needed to enforce the contact constraint. And one important thing about FEBio is that it doesn't actually solve for these Lagrange multipliers directly, but instead uses approximation methods for estimating these Lagrange multipliers. And the two methods that we implemented are called the penalty method and the augmented Lagrangian method, which is in a sense an extension of the penalty method. Most of the contact algorithms share the same basic set of parameters to enforce that contact. And so first off, the most important one I'd say is the penalty parameter. So in the context of the penalty method, you can think of contact basically as a spring that is placed between a point on the primary surface and on the secondary, and its projection on the secondary surface. right? And so that penalty parameter, in a sense, can be thought of as the spring constant of that imaginary spring, right? And so in the penalty method, the force, the contact force, is basically the product of that contact gap multiplied by that penalty factor. So what happens with augmented Lagrangian? So the augmented Lagrangian basically does that penalty step in the first augmentation, as we call it. So the first time that FEBio solves a time step, it'll apply that penalty method to get an initial estimate of that contact force. And then the augmentations will kick in. And what that means is that it's basically, FEBio is going to try to ratchet up that Lagrange multiplier, try to decrease that gap function. And usually the augmented Lagrangian method is fairly good at doing that. So in order to enable that, you have to set the log on parameter to 1. And just as an aside, there is one contact interface that allows you to set option 2, which is a true Lagrange multiplier method, and that is the tied node on facet contact. So that contact interface does have an option to solve for the Lagrange multipliers directly, in which case that the penalty does not come into play. So this augmentation is an iterative method, so you need to have some criteria to stop it. And there's a couple different options. First, you can set the tolerance, which basically measures the relative change in these approximate Lagrange multipliers. So once that relative change drops below the threshold, then the augmentations are considered converged, right? So in addition, you can also set a minimum and maximum number of augmentations. There's more parameters that you can set, but these are, I would argue, the most important ones to know of. Okay, so that was a quick recap. I hope this was clear. Again, if you want to learn more about that, I remind you we have a first webinar on contact where we talk more about these concepts. But let's move on and talk about debugging contact problems. So the two most commonly problems that users run into are the contact is not sufficiently enforced. Now I call this the easy problem because usually using the parameters of the previous slide, you can get that contact gap decreased by quite a bit. So the second problem, which I call the hard problem, is problems with convergence of these of contact problems. Okay, so let's take a look at these problems separately and see how you can address those. So let's start with the easy problem, and that is that the contact is not sufficiently enforced. So what's the main cause of this? So you have to keep in mind, think back of the penalty method where the contact force is essentially the product of that penalty parameter times the gap. So that implies that you can't have a force unless you have a gap, right? So there's always going to be a little bit of gap when you're dealing with FEBio's contact formulations. There's just, usually it's very difficult or impossible to get that gap to 0. So the challenge here is, well, how do you pick a penalty parameter that is going to give you a good enforcement of contact? So you have to keep in mind that the penalty parameter essentially has units. You know, it's basically a traction over a length. And so it's going to be affected by the stiffness of your material. It's going to be affected by the size of your mesh. And so picking that parameter might be challenging. So what are some of the solutions you can do? So first of all, there is a flag called the auto penalty flag. And what that flag does is basically it takes the stiffness into account, it takes the mesh size into account, and tries to give you a good initial estimate of a penalty parameter. Now with that flag on, you can still set the penalty factor yourself, but in that case, the penalty factor now becomes a scale factor to that auto penalty parameter. So that usually gives you a good starting place for playing with the penalty factor. So there is also a new parameter called the update penalty parameter, and that one is very similar to the auto penalty, but in addition, it's going to recalculate the auto penalty during each time step. And that can be helpful for problems that stiffen or soften considerably during the analysis. Think of a fibrous material. Usually fibers have kind of an exponential stress strain curve. So they're very soft initially, but they might stiffen significantly during the analysis at larger strains. And so that initial auto penalty factor, which is based on the initial stiffness of the material, might be fairly low. It might not be sufficient to enforce the contact during the stiffer part of the simulation, right? So for those kind of simulations, I would also recommend setting that update penalty parameter. And then there are also the augmentations, which you can turn on. And as I said, the augmentations, what they do is they really try to ratchet up that contact force and try to decrease the contact gap. So in the last webinar, I kind of showed a more detailed analysis. I reproduced this graph here from the last analysis, so I'm not going over this again. As I said, this is usually the easy problem. So let's focus now on the hard problem. Contact problems that struggle to converge. So the first thing I have to say is that when your model is not converging, it is not necessarily the problem of the contact formulation. There are many reasons why your model will not or struggle to converge. You can have, if you have thin structures, there can be buckling going on. There can be softening of the material. If there's damage evolution or something like that. So there's many reasons why a finite element problem would not converge. But assuming you've been able to eliminate all other causes and your suspicion is that the contact is the problem. So here are some of the things that you can look at and see if they might be the culprit for what's going on. So first of all, it's important to understand that some of our formulations produce a symmetric matrix, whereas other formulations produce a non-symmetric matrix. This is something that you need to know, and you can find this information in the user's manual. But the sliding elastic, which is the most commonly used formulation, is in fact a non-symmetric formulation. And so you would have to set the non-symmetric flag. You have to set that flag in two different places, and I'll show that in a minute. So sometimes when the contact is evolving rapidly, it runs better if you use the full Newton method. And again, I'll show you in a second where you can find that setting. Other things you can try is reducing the time step size, so increasing the number of time steps, but use smaller time step sizes. The other thing to understand is that if you have too much penetration, then you may also have convergence problems. And the reason for that is because many of the contact formulations actually assume that that contact gap is small. In fact, it's that assumption that leads to a symmetric formulation for the node-on facet and the facet-on-facet contact formulations. So when that gap is large, then the implementation produces a poor approximation to the stiffness, and you can get convergence problems. The other thing is that you can try to enforce the contact too strongly. Like I mentioned, you will rarely be able to get to zero a contact gap, and if you try to enforce it too strictly, then you might also have convergence problems. Penalty factor too large can also cause problems, because if the penalty factor is too large for a given gap, you might be generating very large contact forces, which may result in inverting the mesh. There can also be complications with the projection algorithm. So the projection algorithms, remember, are the algorithms that try to detect where contact is happening. So you can have if you have a complex geometry, sometimes it's difficult for the contact projection algorithms to identify the correct contact pairs. And the two parameters that can help there are the search radius, which basically defines the radius of, or for each point on the contact surface, on the primary surface, it basically defines a radius, and only the facets on the secondary surface that fall within that radius will be considered. And somehow, and this can be very helpful when you have complex geometries. The other parameter that you can set that might help with convergence is the seg-up parameter. So basically every time the mesh updates, the contact projection algorithms have to re-evaluate the contact situation. And it can happen that a projection node kind of flip-flops between two different facets on the secondary surface. So with the setup parameter, you can basically set a maximum number of projections that FEBio will do, after which it will just stick to whatever facet on the secondary surface that the contact point was projected to. And so that eliminates that flip-flopping and can help with convergence. Okay, so enough said. Let's put this now into practice. Let me open up FEBio Studio here. Okay, so there we go. So first of all, these problems are available on the repository. So if you open the repository, so under webinars, webinar on contact part 2, you can find all the example problems that I'll be showing today. So we'll start with the sliding error example. So the model that I've set up here is basically, we have this orange half cylindrical part that will first move down and then slide across the yellow part. So if you run this model, you'll see that it will not run. So we have a contact problem that is not running. I don't think that anything else is the problem. This is a very simple problem, so there's no buckling or softening going on. So it's the contact that is the issue here. So let's use some of these tips here to help us figure out what is going on with this problem. First, let's take a look at the log file and see if there's any helpful information there. So this says that the problem error terminated because of a negative Jacobian, right? So a negative Jacobian essentially means an element was inverted. Okay, is there anything else that might help us identify what the cause is? So at the top, there's this warning that says the sliding elastic contact algorithm runs better with the non-symmetric stiffness matrix. So as I just mentioned, this contact formulation requires or generates a non-symmetric stiffness matrix. So let's turn that on and see if that helps. So remember, there's two places where you have to set the symmetry flag of the stiffness matrix. The first is in the contact formulation itself. So under the properties, so if you select the contact formulation in the model tree, under the properties, there is a symmetric stiffness flag. So let's set that to no. And then the other place you have to set it is in the step settings. So here on step 2, if you scroll down to the linear solver settings, there's a matrix symmetry option. So you would also set that to non-symmetric. Okay, so let's see if that helped. It did not. Okay, so that was not the issue. Let's see what else the problem can be. So are we using auto penalty? The answer is yes, we're using auto penalty. We're using our non-symmetric stiffness matrices. So the search radius, as I mentioned, can help for complex problems. In this case, I don't think there's any problem with the projection algorithms. So I doubt that is going to help. The segment updates here. So we've set that to 4. So the default value is 0, in which case that FEBio will always do segment updates. So this was already set to 4. It didn't seem to help. So what else can we do? Well, the clue that we got here was this negative Jacobian, right? So some of the elements are inverted, and it helps us to see which elements are inverted. So when you run FEBio, you can run FEBio in debug mode, right? In the run FEBio dialog, there are advanced settings here. If you check the debug mode, what FEBio is going to do, it's going to run the model again, and it's going to store all the non-converged states to the plot file as well. So let's give that a try and see if that helps us identify what's going on. So when a model error terminates, FEBio Studio will not immediately give you the option to load it, but you can still load it by either double clicking on the job name here under the jobs, or by clicking on the plot file icon. So when you open this plot file here, you can see now on the timeline that there are additional time points here. So the first one, the green one, is just the initial configuration. And all these yellow ones are the non-converged states of the first time step. And we see that the last one here, indeed something is going on. Now notice that it's the elements on the yellow part that are inverting and not on the orange part. So why would that be? If we go back to the model, we notice something, namely that the first material has a Young's modulus of 10,000, whereas the second one is a Young's modulus of 1. So the second material is much stiffer than the first one. So if we have a big discrepancy in stiffness, we have to take a closer look at the penalty parameter settings. So in this case, we're using auto penalty, but you have to keep in mind that the auto penalty is calculated on the primary surface. So which one is the primary surface? The primary surface is the stiff one. So the result of picking the stiff surface as the primary surface is that the auto penalty is going to generate a very large penalty. So large, in fact, that in this case, it's going to invert elements on the softer side. Okay, so that's great to know. So there's two things we can do. We can either lower the penalty factor, or what we can do here, and this is what I would recommend in this situation, you can swap the primary and the secondary surface. So to swap the primary and secondary surface, you simply right-click here on the contact interface and click the swap primary secondary. So now if we run this again, it takes about 20 seconds, I think, so not too long, but as you can see, we're already getting much further. In fact, we're getting a normal termination. So we left the debug mode on, and so this is why you see all these yellow states here. So these are all the nonlinear iterations for each time step, and then the green state at the bottom is basically the converged state for that time step. So that's great. So let's take a look at the contact gap, and the easiest way to do that is by just adding a plane cut to your model. And let me change the orientation of that plane cut like that. Turn off the plane itself. So the model ran, but we're having quite a bit of penetration, but that's great because that kind of reduces the problem to the easy problem. So now we can play with penalty parameters and augmentation. And so let me just show you that we can get some really good contact here if we increase our penalty parameter. And in addition, we'll turn on the augmentations. So let's run this one more time. I'll turn off the debug mode. It'll take about 20 seconds to run. Let's see, it's almost done. And we should be about done by now. Okay, perfect. So hold on before I load. So let me show you. So this is what we had. If you look at the contact gap, we have here 0.09. So let's see how much did we improve. So now we are at 7, let's say 1 times 10 to the negative 4. So we're doing pretty good on this contact enforcement. Okay. So I hope that kind of gives you an idea of the steps you can take to debug your contact problem to kind of figure out what's going on and how you address them. Okay, so let's move on to contact with different types of element formulations. So first we'll talk about contact with shells. And so first of all, what is a shell? So a shell is basically, it's still a solid, still represents a volume, but it has a very thin dimension compared to the other dimensions. And because of that, it's usually more convenient to represent this as a surface mesh and then a scalar shell thickness value that tells you how thick the shell is on different parts of the mesh. So in addition to the surface and the shell thickness, you also need to know what that shell surface actually represents. Does it represent the top surface of that implied volume, the bottom, the mid surface, or anything else? And so in the recent shell formulations in FEBio, that shell surface is the top surface. All right, so this was different from older shell formulations that we have in FEBio, where the shell surface was the mid surface. So the shell surface represents the top surface, and as the volume of that shell is kind of defined by growing that shell inwards by the shell thickness. So in FEBio Studio, you can actually, at least on the post side, you can render these shells as solids, and I'll show that in a minute, so you can kind of see better what volume that the shell actually represents. Now, because the shell surface represents the top surface, usually you don't have to do anything special when using shells in contact. There's only a few scenarios where you have to pay attention. So first of all, you do need to know in which direction that the shell normals are pointing, because the shell normals are pointing to the outside of the shell. So contact happens when a node ends up on the negative side or the inside of the shell, right? So it's important to know in which direction that these normals are pointing. Now, there are some situations in which that, regardless of which direction that shell is pointing, you cannot define contact properly without additional flags that you have to give to the contact formulation. And so, I show here a case on the right where solid B is on the positive side of that shell. And so for that contact there will not be any problem. But for solid A is on the inside or the negative side of that shell. And so if you try to run contact, the contact is going to try to push that solid A towards the positive side of the shell, most likely causing very large deformations and inversions, element inversions. Fortunately, there are a few flags that you can set to help the contact algorithms interpret the situation correctly. And so, in fact, there's the shell bottom primary or the shell bottom secondary flag that you can set depending on whether the shell is the primary or the secondary surface. Okay, so let's take a look at an example problem. So here we have such a situation, except that we're dealing only with shells. So the yellow parts are going to be moving up and down. The left one is going to move down, the right one's going to move up, and then the orange part is constrained on its outer ends. There are two contact interfaces defined between the shells, namely a contact with the left yellow part and then the contact with the right yellow part. Now, first of all, I said that the normals are important. So how do you visualize the normals? Well, if you right click on the graphics view here, there is an option here that says show normals. If you click on that, FEBio Studio will render the normals on top of the geometry. You can set the scale of these normals. If you right click, go to options, under display settings, you can set the normal scale factor. So let's change it to a 0.2. So now you can see that for the left contact, the shell normals are pointing up, and the shell normals of the yellow part are pointing down. So they're pointing basically towards each other. So for that contact interface, everything already looks fine. The other one, on the other hand, is problematic because it is on the negative side of the orange cells. So for that contact interface, the second contact interface here, we'll have to set that flag. Now, in this case, the orange shell, so we'll have to know, so the primary is the yellow shell and the secondary surface is the orange shell. So we want to invert the normals on the orange shell, or we want to tell the contact interface that we're contacting that shell on its bottom side. And so we have to set the flag use the shell bottom on the secondary surface. Okay, so that will tell the contact interface that the primary surface will be contacting the secondary surface on the bottom side. Now, FEBio will take care of all the logic that is necessary to flip the normals and take the shell thickness into account. So we should be able to run this. And so this will take about 20 seconds to run. So once this is loaded, I think, okay, perfect. Okay, so let me turn off the normals here. So let's see what happened. So remember again that the shell surface defines the top surface of that implied volume. So for the left contact interface where we don't have to do, we indeed see that we get contact directly on the shell surfaces. The right one shows that the contact is actually occurring at an offset from the shell surface, right? So remember, we are contacting here the bottom part of that shell. And so the contact algorithm took the shell thickness into account to make sure that the yellow surface does not penetrate that implied volume. Now for shells, it's often helpful to visualize these shells as solid elements. So how would you do that? So if you go back to the top item here on the View tab in the Post panel, and you can set the option here, shell as hexes. This should say shell as solids, because this would also work with triangular surfaces. So we set that to yes. Now in addition, we have to set what the reference surface is. So for our shells, this is the top surface. And you can now see indeed that the contact is properly being applied. So on the top surface in the left and on the bottom surface on the right. Okay, so those are kind of the only complexities that you would run into when you're dealing contact with shells. So let's talk about some other element formulations, namely the higher order elements. So in principle, there shouldn't be any problems with using the contact formulations with higher order elements. The only caveats there are that, first of all, there are a few contact algorithms that don't support higher order elements, and those are the sliding node-on facets and then the tight node-on facet. And that's because they are using nodal integration rules for which we don't have any higher order integration rules implemented in FEBio. So when you're using higher order elements, I recommend using the sliding elastic, or if you need to, you can use the sliding facet to facet. And then for tight interfaces, you would use tight elastic or tight facet to facet. So a few years ago, we actually did a study on using quadratic elements or quadratic tetrahedral elements, I should say, in contact. And the context of the paper was articular contact, but I think a lot of the findings that we had in that paper apply to more general situations as well. And so if you want to learn more about some of the consequences of using quadratic elements in contact, so I will refer you to that paper. Now, one of the things I want to point out is that for these higher order elements, the default stress recovery method that we use for the linear elements doesn't work very well and doesn't always give good stress predictions. So the problem is that FEBio basically only evaluates the stresses at the integration points. But for post-processing, it's more convenient to have the stresses at the nodal points. So there has to be some way to project these integration points from the integration points to the nodal points. And so what we do with the linear elements is we basically average the integration point stresses, and we assign that averaged value to the elements, and that goes into the plot file. And then FEBio Studio does an additional smoothing step where it takes for each node the average of all the surrounding elements. Now, there's a lot of averaging going on, but if you have a sufficiently refined mesh, usually that doesn't cause any problem. And for linear elements, this usually produces good predictions of the stress. For higher ordered elements, that is not always the case. And so we implemented a different recovery method, which is called the SBR stress. So SBR stands for Super Convergent Patch Recovery Method. And so that method, projects the integration points to the nodes by using a least square fit, local least square fit around the node. And so that actually produces pretty good stress predictions for higher order elements. So let's take a quick look at that, what that would look like here. So let me pull up the TET10 problem. So again, it's like our sliding problem that we saw before, but this time, let me start running this because I think this will take a minute to run. So, so again, the orange parts will go down and then move across the sliding interface. These are 10-noded tetrahedral elements. If you open the mesh inspector here, you'll see that we have 10-noded tetrahedral elements on the bottom, and then we have 20-node hexahedral elements on the top. Now the top is a rigid body, but the reason why we're using here 20-node hexahedral elements is that so we can approximate that curvature of that cylinder very accurately. Otherwise, we would have additional faceting of the contact interfaces. And so by having that very smooth surface, we can have any contact issues will be, the result of these 10-node tetrahedral elements. So once this runs, and we're almost there, okay. So this model ran, and as you can see, like it goes down and then slides across the interface here. Let me turn off the indenter. So let's now take a look at these different these different stress predictions. So first of all, I want to draw your attention to the data tab here. So the stress value here, which is the usual stress prediction or projection algorithm that we use, you can see here that this comes in as an element variable using an item format, which just means there is one value per element, right? And you can see that if we turn off that additional smoothing that FEBio Studio does. So let's plot, let's say the third principle stress here. So you can see that indeed you get, a single value per element. And so FEBio Studio, in order to get a smooth field, FEBio Studio needs to do additional smoothing on that. However, the SBR stress here also comes in as an element variable, but has a node format, which means that it has already projected the stresses onto the nodes of that part. So if we look at the third principle stress, and again, we're not doing any averaging here, we see that we're already getting a very smooth representation of that stress. And in fact, if we go back, we'll see that turning that nodal smoothing on or off has no effect for the SBR stress because it's already a nodal variable. So when you're dealing with higher order elements, I recommend that you include the SBR stress in your model. And to do that, I have to go back to the model here. Under the output section, there is the plot file item. If you click on edit the plot variables, you get the output window where you can customize the output of the plot file. And so if you type in stress, you can see all the different stress measures that you can use. There's the SBR stress, which I just show. There's an SBR P1 stress, but that has no effect for 10-noded elements. It will produce the same thing for 10-noded elements, but might produce a different prediction for 50-noded TETs. There's also a nodal stress, which we've found to give often good predictions of stress. So there are some situations in which the SBR stress does not work well, especially when the structures are very thin. The reason is that it does a least square fit, and in order to make that least square fit, mathematically well defined, there has to be a minimum number of integration points around that node. And when your structures are very thin, that cannot always be guaranteed. So if you see anything odd in the SPR stresses, that's probably the case, in which case you can try the nodal stress as an alternative. Okay, that's all I wanted to say on the higher order elements. So let's talk about some specialized contact situation. So first up, contact with friction. There are two sliding contact interfaces that support friction, namely the sliding elastic, which again is the one I would recommend to start with unless you have a good reason not to. But there's also the sliding node-on facet that, that also supports friction. So they implement a simple Coulomb friction model that has the same static and dynamic friction coefficients. One thing to keep in mind when you're dealing with friction is because friction is a dissipative process, the problem becomes inherently path dependent, right? And so that means that you'll have to pay attention to the effects of your time step size and your element size, and you'll have to do some sensitivity studies to find out how accurate your stress or your contact predictions will be. So in the project file that I included on the repository, there's a project file there. So when you open that, you get all these example problems. And so there is an example that uses friction. So in this case, so we just have a block that's going to be pushed down and slip across that yellow part. So it's a sliding elastic contact. The friction parameter can be set right here. So the friction coefficient. So let's set that to 0.2 and then run this model quickly. There we go. So now we can see the effect of adding friction to your model. So now the block kind of gets dragged across that interface. And just for comparison, let's just run that quickly without the friction. So if we turn friction off, we see that there is no dragging effect on that block. Okay, next up is self-contact. So self-contact happens when a surface basically folds onto itself. Now, in principle, there isn't really any complication here because you can still set up a primary and secondary surface and use the contact algorithms as you would ordinarily use them. But you can imagine that when the geometry gets complicated, it might not be easy to identify the primary and secondary surface. So fortunately, all the sliding contact interfaces support self-contact, and it's very easy to set that up. You just have to assign the same surface to both the primary and the secondary surface. So one word of caution is do not use the two-pass method for self-contact. So what the two-pass flag usually does is it runs the contact algorithm twice, where it flips the secondary and the primary surface. So since the primary and secondary surface is the same in this case, the two-pass flag will not do anything except slow down the model, right? So that's the only thing that I would recommend. Make sure that two-pass flag is off. So again, we have a simple example here. So in this case, we have two contact interfaces set up. So there's going to be self-contact on the top surface, and there's going to be self-contact on the bottom surface. So again, the way you would set that up is by assigning the same surface to both primary and secondary. So let me select that surface. So this is the bottom interface at the bottom surface. And then for the secondary, it is the same surface. Okay, so that's how you would set up self-contact. Let's run that quickly. And you can see here that both on the top surface and both on the bottom surface, contact is enforced. Okay, so fairly easy to set up. Let's Let's talk about sticky contact. So sticky contact is, it's a variation of the tied node on facet contact algorithm. And it modifies that tied contact algorithm in two ways. First of all, it does not establish the ties until there's actual contact made, right? So in the usual tied interfaces, it is assumed that the contact occurs or the tie occurs at the initialization of the model, right? So at the very beginning. So nodes that are in contact will be tied. Nodes that are not in contact will not be tied, and it will stay like that for the rest of the simulation. So with the sticky contact, that's not going to happen. So contact is not going to be established until the primary and the secondary surface actually make physical contact. The second way it differs from the tied interface is that it also allows you to break that tie. So there is a criteria in there that specifies a maximum traction. So if the contact traction would exceed that threshold, then the tie will be broken. So you can use that to kind of peel off two surfaces from each other. And also in situations where you're dealing with high friction contact, so where the slip between the surfaces is not significant, it's often better to just use a tied interface, and then you can either use the tied interface or the sticky contact interface. So let's open a quick example here. So in this case, we have this orange part, which is laying on top of the yellow part. Now in this case, we do have contact from the beginning, so the tie will be established at the beginning. But what's going to happen is this purple block, which is a rigid body, is going to be pulled up, and basically it's going to be peeling off that orange part from the yellow block. So first of all, how would you set this up? So if you right click on the contact item here, you can say add contact interface, scroll down, find the rigid wall, sorry, not the rigid wall, the sticky contact, and it's already in there, so I'm just going to cancel that. And then on the sticky contact, you would set that up basically like any other contact, but it does have two additional parameters here. It has that snap tolerance, which is kind of a tolerance on the displacement or how close the nodes have to be before they're before the tie is established. And then there's the max traction parameter, which basically defines the maximum traction threshold at which point the tie will be broken. So let's run that model quickly. Okay. So here you can see if I run the animation, you can see the yellow part, the orange part is getting kind of peeled off of that yellow part. Okay. So next up is the rigid wall contact, and the rigid wall contact is useful when all you're interested in is contact with a flat rigid boundary. So although this is called rigid wall contact, it has nothing to do with the rigid body, so you don't need to set up a rigid body. In fact, you don't need any mesh or geometry to define that plane. The plane is defined implicitly through its plane equation. So basically, a normal and a distance to the origin. So in addition, you can also move that plane up and down, so you can give it a normal displacement. And that can be helpful for, if you want to apply any kind of squishing, as we'll do in this model. So let me show how that would work. So here's the rigid wall example. Okay, so how would you set that up? So if you, again, all the contact interfaces are in the same place. So you right click, add contact interface, scroll down, select the rigid wall. Then under the properties, you can see that you have here the normal. You would set the normal of that plane and the distance to the origin. And then in addition, you can set the plane displacement. right? So it's set to a value of 1 here, but there's actually a load curve attached to that parameter. So I open the curve editor here, and then if we only look at the load curves, then you'll see here there is the rigid wall plane displacement. And so what we're doing here is we're ramping that displacement from 0 to 0.5 and then back down to 0. Now, notice that the rigid wall also uses the penalty or augmented Lagrangian method. So you have the same parameters here to control the enforcement of the contact. So there's the penalty factor here as well as the augmentation parameters. So let's run this quickly. Okay, you can see, you can't see the plane here. We'll probably add that in the next iteration, that the rigid wall will also show up on the post side, but you can see that it's doing what we asked it to do. Okay, so finally, I just want to mention this. I'm not going to talk about this too much, but I want to mention that all the contact interfaces that we have shown up to this point only apply to elastic contact, so an elastic on an elastic material. Now, FEBio supports different kinds of physics, biphasic, multiphasic, and several other types of physics. And so usually these type of physics have specialized contact formulations for those scenarios. So when you have two biphasic materials contacting, you would have to use a biphasic contact. So either a sliding biphasic or a biphasic tied interface. So what these specialized contact formulations add is basically they also, in addition to enforcing the contact, the elastic contact, it's also going to enforce continuity on other variables of interest, for whatever physics you're trying to model. So in a biphasic model, it's also going to enforce continuity of the fluid pressure and of the normal fluid flux. If you have a multiphasic analysis that has solutes in there, so it will also enforce continuity of the solute concentration and the normal solute flux. In addition, these contact formulations also automatically define the free draining parts of the surface. So the surfaces that are not in contact will automatically be set to free draining. And this is actually a very useful feature in our contact formulation that is, from what I understand, much more difficult to address in some other fine element applications or fine element softwares, right? So, but since this is a bit more of an advanced topic, we'll probably revisit this topic after that we had a webinar to talk about biphasic and multiphasic problems. So that brings us to the Q&A session. So let me open here the window and see if there are any additional questions. So if you have any additional questions on contact, please type them now into the Q&A answer window, in the question and answer window. So I'll take a quick look at some of the other questions that have been asked. Okay, so there was a question that can the search radius and auto penalty options still be changed in the FEB file for these formulations, these contact formulations? And the answer is yes. So if you're not very familiar with how FEBio Studio works, we have a first webinar that kind of explains what's going on with basically when you run a model, FEBio Studio generates an FEB file. And so you can get to that FEB file and make any changes manually and then run that file through FEBio. So George, you want to answer this live instead of typing the answer?
Yeah, so in terms of biphasic contact, if the rigid body that's contacting a biphasic material, if the contact area is smaller than the entire contact surface of the biphasic material, then yes, you want to use a biphasic contact interface, because in that case, you want automatically to set the fluid pressure to be 0 outside of the contact so the fluid can escape outside of the contact. In terms of the friction coefficient, the answer is we have implemented it, and we are about to submit the manuscript for review. Once it's been submitted, then we will implement it in FEBio Studio and share the details. But it's already in the code, so if you're dying to use it, just send us an email and we'll show you how to do it.
Okay, thank you, Jared. Is there a way to plot which facets FEBio has detected to be in contact? For example, two complex surfaces that do not perfectly overlap. So I'm currently working on adding some additional contact heuristics, including being able to provide a list of contact facets and additional metrics like when a contact happens, or when a point goes into contact and out of contact. So I'm working on these heuristics because I hope they will be helpful in identifying some problems. And the broader context is that we're working on an auto contact implementation that no longer will require picking the primary and secondary surface yourself. You can just assign the parts. And so in that context, I'm adding several additional heuristics that will hopefully help people identify any problems with contact. So in a future version, this will be possible. So a question here on how to simulate a tendon to bone contact. So if the bone is a rigid body, then I would definitely recommend just using the rigid contact. So unless there is anything else that you want to simulate, like a tear in the tendon, or when the tendon could tear off the rigid bone or something like that, I think the rigid contact is the way to go. If you do want to simulate anything else that requires separating that interface, then you would have to go with the tight or the sticky contact. But if that's not the case, I would recommend just using rigid contact.
Jay, you wanted to answer a question live. Do you want to do that?
Oh, no, I think that's what Steve answered live.
Oh, okay. So I just wanted to mention that you can also choose to output the vector gap as opposed to just the contact gap, the contact vector gap, and then you can plot it as a vector. So it'll show arrows in the direction where the gap is oriented, but it'll only show you at the center of each face of the contact surface. So then you will be able to see, if you have the two contact surfaces and tiny arrows that are joining from one location to the other, you should be able to see which surface was intersected at which location, but just the center of the face, not each integration point. So Timothy, you asked if there's anything we should consider when modeling fibrous materials in contact with deformable bodies. So fibrous materials, like Steve said, they can become very stiff when they're in tension, but whether they're in tension or compression in a particular contact configuration could very much depend on what's the current state of loading. So using the update penalty option will make sure that if the fibers that are in tension, their modulus has kicked in, then it takes it gets taken into account in your contact penalty calculation. The update penalty method is not foolproof, but it's one of those things that you can try if you feel like you're having difficulties with it.
So Gerard, is that parameter new, by the way, in the newest version, or has that been in there for a while?
I think it was like a development feature that we had for a while, but I think we only like made it available recently. Yeah.
Okay, so to users, if you don't find that option, you'll probably have to update to the 1.4 release version that we released it on Monday. We do plan to have a patch release later this week, so if you can hold on to the end of the week, then you'll have the latest release version with all these new features. Okay, if there are no more questions, let's go ahead and wrap up the webinar. So first of all, I want to say thanks to my colleagues here of the FEBio project. So, thank you for being here today and helping with answering the questions. I also want to acknowledge our funding sources at the NIH who have made FEBio and all the work around it possible for many years. I think, we started getting the funding in 2009, so over a decade now. So we hope that they will continue to fund this work, because we're definitely not done with adding new capabilities. If you want to know more about FEBio, the best place to go is www.febio.org. So you can find the software downloads there. You can also find our knowledge base there, which has the manuals, tutorials, and also these webinars. So the video of the webinar will be made available on the knowledge base as well. We also have a forum, and to find that, I suggest just go to the support page on febio.org. The forum is probably the best place to look for answers if you have any questions. So some of the questions you have may already have been answered. But if you have any new questions, I suggest to post them there. However, if you do want to reach out to us via email, the best place or the best way to do that is info@febio.org. I also want to remind you that all the FEBio and FEBio Studio software is available on GitHub. So it's all open source and you can download it from GitHub. To stay up to date on FEBio news, there is a news panel on febio.org, but I think Twitter is probably the best way to do that. So just come find us at FEBio software and follow us there. And then we also have a YouTube channel called FEBio Videos, and we will also be posting this webinar on that YouTube channel. The previous webinars are already there, and so we'll probably upload this one as well in the next couple of days. So with that said, I would like to thank all the participants for the webinar. I hope that you found it helpful and informative. Please remember to fill out the survey. We really appreciate your feedback. It helps us a lot in kind of tailoring these webinars to your needs. So we hope that you take the time to fill out this webinar, the survey. And then thanks again and have a great day. And we hope to see you again in the next webinar. Bye.